After 20 years of development and 2 weeks of the most complex deployments ever attempted in space, the James Webb Space Telescope is now fully deployed. Even though the deployments were the riskiest part of Webb's commissioning, getting the optical system to work is equally critical. All 18 of Webb's hexagonal mirror segments must be aligned to within 10 nanometers of each other to form a single primary mirror. And that requires making ultra-fine adjustments as small as 1/10,000th the width of a human hair. This is a slow, meticulous process called phasing. It will take about 3 months to fully execute, but when it's finished, Webb will behave much like any other telescope. The telescope part of Webb is called the Optical Telescope Assembly, or OTA for short. The primary mirror's job is to collect as much light as possible. The more light it collects, the fainter the objects it can see and at higher resolution. The primary mirror has a concave shape that sends light to a convex-shaped secondary mirror. The secondary sends the beam into the aft optical system, or AOS. And by the way, this is the same structure that had that famous lens cap covering its aperture. It even said removed before flight, which in retrospect was definitely a good idea. So far, Webb's optical layout resembles the classic Cassegrain telescope design, which uses 2 mirrors to form an image. However, this image is not fully corrected. In fact, it's purposely quite blurry. And that's because Webb is actually an advanced 3-mirror anastigmat telescope. The cool kids call it a TMA optical design. This configuration sends a portion of the total image through the AOS opening to a concave tertiary mirror. The tertiary forms the final image that is fully corrected for astigmatism, coma, and spherical aberrations, all while precisely controlling field curvature. And this design gives all of Webb's science instruments an equally sharp image of the sky. Although the image is now in focus, it's still a little shaky, and that's because reaction wheels are always spinning to keep Webb on target. And this introduces residual vibrations into the telescope. And that's why Webb carries a 4th mirror called the fine steering mirror. It's a flat mirror that acts as an image stabilizer. The FSM continuously tilts in the X and Y directions as frequently as once every 64 milliseconds. That's 16 tiny tilt adjustments every second. From there, the final stabilized image is sent to the science instruments. At least, that's how it's supposed to work, but we're not there yet. Webb's mirrors must operate at temperatures as cold as 35 Kelvin, and all 18 of the primary mirror segments must be aligned to within 10 nanometers of each other. But even this quick look at Webb's optical system raises some questions. For example, why does the AOS aperture and the tertiary mirror have those elongated shapes? And why does the fine steering mirror look like a miniature primary? What are those black borders doing around the primary anyway? And what's with all that gold bling? And finally, is Webb really going to be more powerful than Hubble? Well, today we're going to take a closer look at just how Webb's optics work and discover the answer to those questions along the way. But first, I'd like to thank Magellan TV for sponsoring today's video. Planet hunting with the James Webb Space Telescope shows how Webb will explore the details of alien atmospheres in the neighborhood of our Sun. It's just one of more than 3,000 documentaries available exclusively on Magellan TV. New documentaries and series about nature, history, science, and technology are added each week and are presented without commercial interruption. And now, Magellan is offering my viewers a full month of their award-winning content absolutely free. Just use the link in the description of this video. Webb's complex design is ultimately driven by its science goals, which include studying the first galaxies to form in the early universe. But because the universe is expanding, much of that light is shifted into the infrared. But infrared light makes it harder for a telescope to achieve a high angular resolution. Here's why. Resolution is a measure of how small an angle a telescope can see down to and still distinguish details from each other. The larger the mirror's diameter, the smaller an angle it can discern. However, the longer the wavelength of light that the telescope is looking at, the larger the smallest angle becomes and the lower the resolution the telescope gets. The only way to overcome this limitation is to make the mirror even larger. At 6.5 meters, Webb achieves roughly the same resolution in the near-infrared as Hubble achieves in the visible spectrum with its smaller mirror. And you might be wondering, well, why then is Webb considered to be more powerful than Hubble? Well, the answer is a combination of resolution, sensitivity, and wavelength coverage. First, Webb certainly has a higher resolution than Hubble in the near-infrared part of the spectrum. And Webb's near-infrared camera actually has 16 times the pixel resolution of Hubble's Wide Field Camera 3. Second, plunging Webb into the deep cold allows it to detect faint infrared signals without emitting its own thermal noise. And that gives Webb a much higher signal-to-noise ratio in the infrared than Hubble can achieve. Webb's large size means that its optics have to be exposed to open space in order to cool down. And that's a problem when it comes to stray light. The Spitzer Space Telescope was enclosed in a tube that blocked unwanted stray light from reaching its mirrors. But an enclosed design traps and re-radiates heat back into the tube. Spitzer solved this problem with a series of heat sinks, radiators, and cryogenic cooling systems. The bottom half of its tube was painted flat black to radiate heat directly into space. But Spitzer was an 85-centimeter telescope. Scaling that system up to Webb's size would have meant having to sacrifice mirrors and instruments just to fit inside the rocket. And that's why Webb instead uses an open design to allow residual heat to radiate away. But this open design means Webb is going to have to deal with stray light very differently. The primary mirrors are surrounded by opaque borders called frills. They block starlight coming from behind the telescope from reaching the secondary mirror. The aft housing is specially shaped, or baffled, to accept only the portion of the field of view that the science instruments see. And that's why the AOS aperture has that elongated shape to it. It's actually cut to the same shape as the science field. The fine steering mirror is also surrounded by a mask corresponding to the frills around the primary mirror. And thanks to the sunshield blocking the sun, earth, and moon, the brightest source of stray light for Webb is Jupiter. Behind the sunshield, Webb's mirrors cool all the way down to between 35 and 50 Kelvin. At those temperatures, thin glass mirrors are unable to reliably hold their shape. And that's why Webb's mirrors are made of beryllium. Like any other material, beryllium shrinks as it cools. But it's also very stiff, so it doesn't warp as it cools. And once it falls below 100 Kelvin, beryllium stops shrinking and becomes very stable. And that means temperatures can vary by several degrees across each mirror segment, but as long as it never exceeds 100 Kelvin, the mirror maintains its shape. With an atomic number of 4, beryllium is the second lightest metal on the periodic table. That makes a beryllium segment 33% lighter than a segment made of aluminum. However, beryllium is 6 times stiffer than aluminum and is even stiffer than titanium. To see what I mean, here are 3 levers made of titanium, aluminum, and beryllium. When they're all sprung at the same time, the beryllium lever barely shakes and comes to rest long before the other metals. And that's particularly desirable because Webb's mirrors were launched vertically instead of lying on their backs like other telescopes. Now, even though beryllium has great cryogenic performance, they and the rest of the telescope structures will shrink down as they cool. So engineers actually built all of the telescope's components and the mirrors to be a bit larger than they're supposed to be so that they'd all shrink in the cold to their correct size. And because Webb must reflect infrared light, its mirrors are coated with a thin layer of gold instead of aluminum. And that's because while gold only reflects the longer wavelengths of visible light, it's an almost perfect reflector in the mid-infrared. And then, of course, there's the requirement to fold up the mirrors ahead of launch. That's why 6 of the mirror segments are mounted on 2 deployable wings that, along with the secondary mirror assembly, were folded up for launch and deployed once in space. And we talked about the details of the deployments in our last video, so I won't repeat them here. But at the same time, why hexagons? Why not some other shape? Well, hexagons combine into a roughly circular shape, which is what you'd want when you're trying to concentrate light into a central point. Another advantage of hexagons is that they have what's called a high filling factor. And this means the segments fit together without gaps. If Webb used octagonal or even circular mirrors, there would necessarily be gaps in between them, which means the mirror doesn't collect as much light. Each segment is about 1.4 meters across. Together they create a 6.6 meter diameter hexagon from tip to tip. And that six-fold symmetry means that each mirror segment only needs to be shaped to just one of three different prescriptions. But the best advantage of the segmented design is that it won't repeat the same mistake made with Hubble. After it was launched in 1990, NASA discovered to its horror that Hubble could not be brought into focus. It turns out that the outer edge of Hubble's primary mirror was ground to a slightly flatter shape than it should have been. The error was tiny, just 1/50th the width of a human hair, but its effect was enormous. The result was that Hubble suffered from spherical aberration. Thankfully, Hubble is in low Earth orbit and could be serviced by the space shuttle. After corrective optics were installed in 1993, Hubble's vision was fully restored. But Webb is too far from Earth to be serviced, and it can't be returned to Earth orbit for servicing either. The good news is that Webb's telescope and its instruments underwent a full set of optical systems testing in a thermal vacuum chamber to verify that everything was fabricated and integrated correctly. This was a major lesson learned from Hubble, which never had this full optical test before launch. But if you're still not assured, don't worry, because the process of phasing is Webb's ultimate insurance policy. It begins by deploying the mirrors from their launch configuration. At full speed, it takes about 1 day to move all of the segments by just 1 millimeter. That's about the same speed at which grass grows. This is why this initial deployment alone takes at least 10 days to complete. But when it's finally done, the mirrors can then be phased together. Behind each segment, 6 actuators are arranged in a hexapod configuration. They adjust the segment's orientation in not just focus, but in 6 spatial degrees of freedom, including its pitch, yaw, and roll. They can even adjust the segment's horizontal and vertical position in space with respect to the others. Each segment is separated by a few millimeters to allow for these adjustments. An additional actuator in the center of each segment is connected to 6 legs that attach at the hexagon corners. The push-pull action is then able to adjust the segment's radius of curvature, and that means any imperfections in the mirror segments can be individually corrected. Likewise, the secondary mirror can be adjusted in a similar manner, although it doesn't use a central actuator. Webb begins its mirror alignment by imaging a star with the near-infrared camera. Initially, it sees 18 images. One by one, the mirrors are adjusted until the images are stacked in the center. That's a good first step, but the image is still going to be blurry. To really get the segments to combine into a single monolithic mirror, actuators continue to adjust each segment, this time in smaller amounts. After each tiny adjustment, the image's point spread function is analyzed. A point spread function is essentially a plot of a point source's intensity on an array of pixels. The Webb team develops special algorithms that analyze the PSF and work out just which actuator on which mirror segment needs to move next and by how much. The commands are then uploaded to the telescope, which makes the prescribed adjustment, and the process is repeated. With each adjustment, the star gets a tiny bit sharper. The sharper the image gets, the smaller the changes become. At the beginning of phasing, actuators move the mirror edges by up to several millimeters at a time. By the final phasing, they're moving just a few nanometers. And that's just 1/10,000th the width of a human hair. But we're not done yet, because the other instruments are looking at different parts of Webb's field of view. So additional phasing is required as each instrument reaches its operating temperature. Needless to say, this is a very slow and meticulous process, which will take about 3 months to complete. Meanwhile, Webb's science instruments are being brought online as they cool to their operating temperatures. They'll run through a series of calibrations and test observations. One of them, the mid-infrared imager, has to be chilled all the way down to just 7 Kelvin. In fact, the instruments and the kinds of science they will be used for really ought to be in their own video. So yeah, there's a lot of work left to be done before Webb is ready for science. But now that it's fully deployed, most of the mission's risk is now retired. So congratulations to the Webb team, and shine on, you crazy diamond. And by the way, how about these crazy diamonds right here who are helping to keep Launchpad Astronomy going? And I'd like to welcome Adhulks, Michael Anderwald, Mark Arnold, Nicholas Artman, Cristiano Brandau, Dennis Baker, Jason A. Blanchette, Houston Clark, Deepak, Vernon C. Easterday, Andreas Illusion, Lauren Elliott, Jane Holloway, David Hunt, Rick Isaacs, Euyun Kim, I'm sorry, I know I messed up half of these names up already, Roman Martinka, Simon Matthews, Tony McCarthy, Christopher Miracle, Jay Mumford, Barry Scott, Sergasi, Larry Seiden, John Waller, Eric Williams, Benjamin Wilson, Viridius Wolf, Kevin Yeagle, and Yazin. Oh my gosh, I've never had so many people sign up for my Patreon all at once, and I'm so thankful to all of you who are helping to support this channel and keep things going. So if you would like to join me on this journey to this amazing universe of ours, well, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay curious, my friend.